Okay, everybody, let's see. Let's see if I have this right here. Hold on 1 second. Okay. How's everybody doing today? Let's see. I'll do the pop out of things. Let's see. Hello. And let's see. So it's a challenge getting things kicked off. I think I'd have it down by now, but it could be a lot worse. We could be having to do all this in person and going through all this rigmarole. So we'll try to keep that to a reasonable reasonable ruckus amount here. So let's see. I popped the stream out to another menu. Just that should. There we go. All right. Tired. Also tired. Everyone's tired. Yes. Okay. I'm really tired as well, to tell you the truth. So much so that, well, hopefully, let's see how far we get. Lots of homework the last week. So no homework this week, or you were already all set. Hopefully, let's see, not as much this week. Okay, well, I do know that folks in my Intro to Game Programming class have a project due this week, and Game Dev 1 folks have a project due this week. So we're going to try to keep today kind of on the short side. We're going to keep the check-ins sort of extra brief. We're going to do everything sort of extra brief, but introduce some cool and exciting things and talk a little bit about future projects and how we're going to make everything more interactive and exciting, your projects and so on. I know for me that seems like I've gotten some plans here to make things more and more exciting and so on. So, okay. Wanted to review, we talked a little bit last time about starting to think about Project 2, which is based on chapters 1 through 6, basically building on everything that we've gotten so far and moving forward into texture mapping and object loading. So that's going to be the gist of it. You should be demonstrating the proper use of, and what I'm saying here is of modern OpenGL, basically using vertex array objects, vertex buffer objects, and shaders for your rendering. No GL begin, GL end, GL vertex, sort of stuff. It's modern OpenGL. You should have some sort of scene with hierarchy of motion or transformation, potentially animation. There should be some basic texturing demonstrated. Basically, diffuse or texture maps. You should have at least one OBJ model loading. So there's an example of how to load models and the sample code for that actually in chapter 6. So it can be a little bit tricky. It's not the most sophisticated object loader in the world. So whether or not I've run into some things with certain Blender objects, and depending on how you do things and how materials are handled, you can kind of break it. But it's certainly a lot better than anyone who took game engine architecture. We were dealing with Panda 3D egg format models, and that was a mess. But OBJ, we're a lot better off. You should have some sort of OBJ model in your project. And I would like to see, I'm hoping that you can implement interactivity and test using IMGUI. Integrating IMGUI is actually really, really simple. I'm going to demonstrate that today a little as well, on top of what we're going to talk about with the texture mapping and so on. And you should have some other sort of feature of your choosing. Do something with textures, do something with the geometry, go outside the box, do a little bit of research. This is really, now you're going to have almost all the fundamentals of like where sort of like a lot of original game programming was once upon a time, with the exception of lighting. Lighting is going to be our next chapter beyond 6. That's, I believe, chapter 7, and that's yet another big gateway kind of opening technology as far as 3D graphics goes. Right. So yeah, we're going to be pretty far this week, and then there'll be lighting soon thereafter. So, but for today, I want to specifically talk about texturing. All right, let me make sure to get here to texturing. Start back over at the beginning here for everybody who's just sort of tuning in. So once again, yes, this is Computer Graphics Computer Graphics Programming in OpenGL with C++, taught by me, your host, and text as usual, V. Scott Gordon and John Clevenger. And today we're going to talk about texture mapping. So what is texture mapping? I'm sure you've all seen texture mapping done at some point. Not sure, you probably maybe just don't know, if I start talking about the terms like UV coordinate systems or UV mapping or texture unwrapping, all those sorts of things. You might have had to deal with those in certain programs, or if you've done like things in various game engines, you might have dealt with that sort of thing. But we're going to talk really about like how to do it. So imagine this is kind of a complex example of it, but imagine we have a model of a dolphin. We've talked a lot about using using triangle primitives to form models and meshes. In this case, it looks like we have a really nice triangle mesh for this dolphin here. Everything looks nice and closed. It's got smooth surfaces. Everything has lots of wonderful shared vertices, good collinear edges, and so on. Excuse me, just had to wash something down. So that, it's a nice, what we'd call a watertight model. So it's a nicely formed model here, but it has no color on it. It has no, texture to it. We just colored it all one color, it would sort of disappear into the background. Similar to how, like if you've done the simple red cube, you'll notice, okay, without any texture to it, without any variation in color, it just sort of just disappears into the background because it's just all one solid color without shading, without shape and form and so on. Okay, so we really can't see the shape because of the texture or in the absence of any sort of shading. Now, here's two examples of a texture mapped version of that same model using two different textures. One texture being sort of this wonderful, sort of simple checkerboard pattern here, okay? And let's see, I really love to be able to present this in a better, let's see, view, let's see if I can do this. Slideshow, start slideshow. Any from the current slide? Yes, all right, that's not so bad. That actually worked. Go figure. Technology, once in a while it behaves for us here. All right, so let's look at the texture. I wanted to kind of zoom in specifically so you can see this sort of second texture. It's what looks like an odd sort of thing. The first one, pretty straightforward, and actually is quite redundant because it's just a black and white checkerboard, and it's a lot more than is really necessary because really, if you look at it, it's just a repeating texture. If we looked at just one tiny little corner of it where we had black, white, white, black, a simple one iteration through the checkerboard here, we could probably texture this whole model using just one corner of this thing, one tiny little corner. And the texture winds up being repeated over and over and over again throughout the model. But you'll notice it is doing some interesting things, like there is around the area of the eye and the dorsal fin, I'm forgetting the other names of all these ventral fins, the tail, and so on. There's some kind of interesting changes in the texturing pattern that's going on due to how the rendering engine, how the GPU is actually texturing at those locations or at those parts of the mesh. Right? So if we were to look at this using a more appropriate texture, you see this is an unwrapped texture, so it's flattened out. All textures generally are going to be rectangular, right? We're always dealing with rectangular textures. A lot of the time we're dealing with square textures, okay? Certain engines may or may not care about whether they're square or not, and generally we're looking at coordinates that go from 0 to 1, just like, there's 0 to 1 floating point, so they could be interpolated. So we're not worried about, exact resolutions in the abstract sense here. But what happens, in this case here, now we have our dolphin over on the right, looking far more like a normal dolphin because the textures have been appropriately mapped. Right? So we have this part of the dolphin here, which is the main portion of the body, and you can see sort of these kind of cool curved patterns here and this little part that comes down to its ventral flipper fins there, and its dorsal fin would be up here, and going back into the tail, and so, or is it the other way around? Let's see. Yeah, I guess this is probably the tail back here, and this is the front. Okay, so it's, imagine you sort of, and I hate to say it, you peeled the dolphin, or you peeled it and then squished or flattened it out. You've unwrapped the dolphin, and here's what its body would look like if you had sort of, you've probably seen at least on video somewhere, like a bearskin rug or a kind of scary texture of something that's sort of been unwrapped. Or you've seen horror movies where they, yeah. Anyway, so this is sort of what a texture image looks like, a texture map looks like. And it doesn't even need to be contiguous, right? So here's the main part of the dolphin's body, but then the fins are actually over here. They're kind of disjointed between, here's the tail, here's the dorsal fin, here's each of the ventral fins, and actually here's the dolphin's eyes. Right? So they're not all contiguous on here, because any triangle, any polygon on here has a set of UV coordinates, a U and V, which is sort of like an X and a Y, but a U and a V, into this texture image to say where the texture for that polygon comes from. And then it will use our interpolation that we saw, even in terms of color and the interpolating color between vertices and so on. We can interpolate the positions of the texture depending on what the UV coordinates of each polygon or each vertex in a polygon are. Okay, so this is a texture map, and then there is a vertex UV for every, a U and a V value for every vertex, in addition to the X, Y, and Z, the position of each vertex. So that UV coordinate tells us where that corner, where that vertex on this would draw its texture from this texture map. And then in between, it would interpolate a location for that from here. Okay. So in order to set that up, let's talk about the individual components of that. So there are several mechanisms that need to be coordinated to support texture mapping. It's not quite as trivial as just having, a U and V coordinate, right? You have a texture image. That's your kind of albedo or diffuse texture. In this case, we will have other types of textures or other types of maps that we'll use for other things in future shaders. But for now, we just have a texture image that will have the diffuse color information for the appearance of the object. There's going to be a texture object that's going to hold the texture image. Okay, here we're only looking at 2D images. And then here's one of the magic pieces of it as far as OpenGL goes. There is a special uniform called a sampler. All right, the sampler is basically a variable so that the fragment shader can access the texture. It's a mapping in between the texture and what the shader is going to be doing. So we can sample the texture, right? We find the proper location on the texture according to the interpolated points and so on. Okay. Now there is a buffer, which is similar to it. It's just basically another vertex attribute buffer, a VBO, that will contain the texture coordinates. That can be something that is interleaved with the other texture attributes, or it can be a separate buffer of its own. So you may have multiple VBOs, or you could have a single VBO that had all these attributes combined in them. That's kind of your choice. In our examples, we're going to have separate buffers for texture coordinates versus the vertex position coordinates, vertex positions, yeah. So there'll be a vertex attribute dedicated to that buffer so that we're going to be able to pass the texture coordinates down the pipeline. Right? So this, just like other VBOs, have a vertex attribute, a description of how that buffer should be interpreted. We similarly have that for a texture now. And on the graphics card, there will be some sort of texturing unit. This is we will assign a texture unit on the graphics card. I think in some cases we'll just assume it'll grab the 0th or first one along the way. You can actually get more elaborate in terms of determining which texture units. You can query the card, your GPUs, for all sorts of attributes and so on. But for now, we're going to probably just see the simple case here. We're going to just be dealing with a single texture unit on the graphics card to do our texture mapping for us. Now, early on, way back when in the early days of the class, we mentioned the Soil2 library. This is a simple OpenGL image library. And that is the library we're going to be using for loading the texture image into an OpenGL texture object. We have to basically be able to load the texture from, load the image from disk, right? From a file. We have to get it into our program somehow. So that's why we're going to use the Soil2 library for that. And there's lots of other libraries, and depending on which examples you might be following, or you might be looking at other tutorials outside of the one in the book, you may see some different image loading libraries in there as well. So if you're following another tutorial, you may want to adapt it to use Soil2. It's pretty simple. Okay. So to load a texture, we just have the name of the texture, and we call soil load OpenGL texture, giving it these flags to say, okay, create a new texture, whether or not it is inverted in the Y direction. So we kind of we have to adjust depending on whether or not it's Y is positive, Y is negative. And then we get back an ID saying, yes, we have a texture, or it did not load. Okay. So this becomes pretty simple. We just say in our samples in the book, we have my texture equals utils, usually in the utils.cpp program that we've created. And we have something called just load texture. So we can load any particular texture. And thankfully, this is where it handles. We don't have to worry about, decompressing files and texture formats and so on. JPEGs are a compressed file format, right? It's not just a simple one or a set of RG and B values, or even RGBA values for every pixel that's, boom, just there in a file. It's actually a highly compressed file format using all sorts of perceptual coding and DCT, discrete cosine transform to, kind of segment the various frequencies within the file. And so on and so on. Image compression, digital signal processing, that sort of thing is a whole subject, of course, in and of itself, and we wouldn't want to necessarily write our own JPEG loader. So that's why we use Soil, so that we can turn this compressed JPEG file into an appropriate format for textures. Now, sometimes, sidebar, there are certain types of texture compression that are often used to kind of maintain and help preserve or manage the amount of texture space. You've probably heard, like if you bought a graphics card, it tells you how much memory is on the graphics card a lot of the time. So we'll see it, anywhere from, these days it used to be, 512 megabytes. Now we have, it's not unusual to have a 4, 8, 16, even 20 and 32 gigabyte graphics card, which is basically a lot of that space is reserved and used for texture buffers, right? So we're using a lot of space on there, and there is an opportunity even to use some internal texture formats or internally compressed texture formats on the card as well to help manage texture space. So just remember that when we're dealing with images, they're not necessarily raw, just single pixel per RG and B, or single value for an RGB pixel or the color component and so on. So sometimes we're dealing with that. That's why we like to use these libraries. Okay, so load texture will take care of the JPEG format for us and give us an OpenGL compatible texture. So now let's talk about where U and V come from, or the texture coordinates, our UV coordinates. So imagine we have a model, which is a cube here, and we have a set of vertices for that, for some triangles on the model here. And at each vertex, normally this might be 0, 0, 1, 0, 0, 1 in terms of the actual model space. Perhaps these might make sense with regards to coordinates as well, if this was a unit cube here. But now what we're also saying in this case is we're saying that U and V wise for this model, we're mapping 0, 1 in the texture to this corner, 1, 0 to this corner and 0, 0 to this corner. So if we looked at this texture image, we would say, okay, this upper corner here, 0, 1, U0, V1, corresponds to this corner up here in the texture image. Okay. And let's see, I should pull, let's see, I just noticed that my presenter view is covering up my chat. So I'm just making sure that the chat is visible for me here. And I also do not see, let's see, make sure, oh, okay, I don't see anything in the Twitch chat. Just wanted to make sure. Occasionally give me a shout out so I know people are still there. Okay, so 0, 1 corresponds to this corner here. 0, 0, this corner here. 1, 0, this corner here. So this first triangle, the green triangle on our screen here, would pull the texture from in between those points. It would take this lower triangle here, which is why we see this image here, this portion. And you'll notice here, instead of this coordinate being, if it was 0, 1, it would pull from that correct place. If this one here were 1, 1, then it would pull from here. And if this were 1, 0 down here, it would also pull from the correct space. But that's not what they're doing in this red triangle. Instead, they've said, okay, this is 1, 1, this is 1, 0, and this is 0, 0. All right. So obviously, these are not world coordinates. These are just sort of arbitrarily kind of rotated by 90 degrees. You know, 0, 0 should be here, 1, 0 should be here, and 1, 1 would be here. So what we wind up with in that red triangle, because its vertices have those attributes on them, we have this kind of 90-degree rotated texture. Okay. Now, if you recall, let's see, axes are often labeled S and T. Well, in my experience, I've seen them more U and V, but S and T also, depending on how things are. You might recall the question came up about when would you have different coordinates or different attributes for the same vertex, right? So this would be potentially one use of that, where what we're having here, we have some vertex attributes that potentially might be different depending on how they were mapped, because we, for some reason, wanted to get this weird result, right? So, you know, I guess it might be compelling to say, well, this should have used the same, in this case with this nice common texture, it should have just gone ahead and used this same attribute, this 0, 1 at that corner, and the same 1, 0 at that corner, and then it probably would have done the right thing. But maybe the texture wasn't laid out that way, so that for some reason we had some different part. Like the case of the, let's see if I can get back to the dolphin, right? Where at some point the dolphin's fins here, it's pulling along this mesh, some of these triangles, some of these vertices are actually going to have a U and V coordinate over here versus these other ones that might be over here, right? At this edge where they meet, right? So this might be the top up here, and then down here might be the vertices directly next to them, right? Because we have this sort of disjointed texture map here, right? So we might have considerably different UV coordinates for neighboring triangles that way, okay? So that's one reason why we sometimes, you know, vertexes that share the same point in space don't necessarily share the same value for a lot of other things, right? So sometimes you'll hear the term texels or textured pixels, you know. So these selected pixels are often called texels. I don't know if we still hear that as much, but you may hear texels, textured pixels, or textures pixels, yeah. So in the example, in the book, we're going to do some things. They have a sample texture, which is a sort of a brick pattern here, and some examples of, you know, how the texture coordinates map to that, right? Now, in this case, you'll notice that in the case of the pyramid, you may not even be using all of the texture on a particular triangle or a particular face. So we might be pulling things like just this kind of triangular shape from a square texture map, right? So here, the front face, for example, might be pulling, let's see, here would be its lower corner, and it would be pulling the texture from 0, 0, then this next corner from 1, 0, then this one would be from 0.5, 1, right? Halfway along the x-axis, whoops, halfway along the x-axis and all the way up on the y. So the third vertex here is using this 0.5, 1, right? So our first face here winds up with using these texture coordinates. And then the right face would use the next and so on. Now, the bottom of the triangle, where we do want to use, excuse me, not the bottom of the triangle, the bottom of the pyramid, however, is a square. So in that case, we want to use the whole texture. So there it would map more directly because we want to use that whole texture. So we take one 90-degree triangle portion of it on that part and the other on that part. So the bottom of the triangle will look correct. All right. So let's jump over to our example of that. Take a look how that actually unwinds itself. All right, so I've got these put together, and here is our textured pyramid. And let me rebuild this. Let's see if I haven't broken it too much here. I have been adding IMGUI to various programs at this point and having all sorts of fun breaking them. So let's hope that this one actually works. Okay. So I've added a bit of a feature here in that I've animated the texture. I have the texture actually flipping back and forth between two textures every second, right? So you can change textures on the fly, for example. And here we're kind of rotating the pyramid, and you can see how if we looked at the textures for that pyramid, let's see if I can show you that. Let's see, chapter 5.1, we have, let's see, the brick texture here, and we have the brick up texture here, which just has a little arrow drawn on it. And we're just flipping between those two textures. Right? Now, the important part is really kind of what's going on in the fragment shader, where if we look at the fragment shader, now it is using this thing called texture, right, which is the texture that we're going to get the information from, and is going to use a sampler to get basically a texel at this calculated coordinate from this sampler, right? So we're really using this piece, which is the sampler here, the texture coordinate, which is something that is figured out by our vertex shader here. All right, see this TC equals text coord. That's passed in just like our position was, but using the next vertex attribute buffer object, right? And then it is, using our our interpolator to go from this kind of just the vertices coordinate to an interpolated version that it's then going to use on, with this sampler to get the right pixel from that texture map. Okay, so it's not very complex shader at this point, but it certainly is doing a little bit more than we had been used to. All right, looks very similar. The program itself is going to look pretty similar until we get into the texture coordinates piece, right? We have layout binding 0. That means that we are having the 0th texture, right? You can set up multiple textures. right? So just like we had a variety of someone, yeah, I should repeat that for the stream. What does layout binding equals 0 mean? It's similar to this location equals 0, location 1, right? Just so then when we're passing in uniforms, we can figure out, passing in vectors and coordinates from the VBO here, we can also bind ourselves to a particular texture that has been set up using this right here. So whenever there's a layout, that means we're binding to some sort of vertex buffer object in this case, or a texture in this case. All right, so we're binding to the 0th texture that's been set up. You'll see in main CPP, let's see, we've got a name of SAMP there. If we look down in here, we have our VBO that contains the normal, the things we're used to, the positions. Then we have the second VBO, which is now containing the texture coordinates, the UV coordinates in that buffer object. And then we'll see here we loaded textures. And then, let's see down in here. Eventually, we are setting the active texture, texture 0. That's why we said binding 0 there, right? This is okay. This texture here is the one it's active, and we are binding it here. So we have the brick texture and brick texture 2, which is one is the normal brick, and the other one is the one that has the arrow pointing on it, right? So that just tells us here, this is texture 2, texture 0, it's active, and that's the one that gets bound to texture 0. Okay? So the magic is really in here, setting an active texture and then binding our texture to that texture there. All right. The nice thing is here in loading the texture, this is also going to be a glue int, so this is really the loading part, so we don't have to worry about that so much. Notice it's not just an image loading library. It is actually loading the texture and giving us a pointer back to that. All right, so let's take a quick look over here at utils CPP, which was where we had set up our shaders, and now we're adding a bit to it, which is load texture. Right. So this is not just loading the file, it's actually loading the texture file and then binding it and generating mipmaps and so on. So we're actually loading that into the GPU, which is why we get just back a glue int to it. So once it's loaded, we don't have to keep loading it over and over again. That just gets set up just once. Okay. And the book will lead you through the specific example of how to get that, or how to develop that load texture function in there to get that loaded. So there's a lot going on here. That's why we wind up with this glue int. Normally a glue int is an index to some sort of object that has been created on the GPU for us that we can then just refer to. We don't have to load again and over again. We just refer to that texture. It's up on the card. Something's just there to be used, which is why there's no hiccup here when I'm changing textures, for example, right? Because I'm just saying, okay, OpenGL, here's your index of the texture that you want to use whenever we're referring to that, right? We're not loading a new texture here. We're just binding the one that's already loaded to this active texture, to this sampler effectively, right? Yeah, just like you notice here, we never really say, I guess this is a good example of it here. You'll notice nothing is called pos or text coord in our program here, right? Because we're referring to those according to the buffers that they're bound to, right? And that's similar to how we never have something that we're referring to as, you know, SAMP, because we're really getting it from just the fact that we're binding to texture 0 there. Right. So here's the bits of it. We are similarly, whoops. Okay, so just like you're used to, we would, we have in the program, we have our texture coordinates. Sorry, we have our normal coordinates. Oh no, sorry. This is the texture coordinates. Texture coordinates into a VBO, almost exactly like any other type of texture data, or excuse me, not texture data, vertex data, like we had the vertex positions, right? We bound the buffer, we told it which buffer object we're talking about here, and we pushed the UV texture coordinate data into that buffer, right? Then sent to the shaders as a vertex attribute, and therefore they will be interpolated. That's the cool thing, right? We don't have to figure out the coordinate of every particular texture or pixel or texel. It's interpolating in between the ones that we specify for the vertices. So to access the texture object within the shader, we are going to use this sampler, right? It is in our case, it's a sampler 2D. Most of the time, you're going to see sampler 2D, which is just a straightforward texture map. We're going to call it samp just so that we can refer to it as something in our shader, and we tell it it is the binding 0, right? The layout qualifier states that this variable accesses texture unit 0, right? Binding equals 0 means texture unit 0. And in here, we see, okay, texture 0, that is texture unit 0 here. Right? So we activate that, we bind our texture to it. So then in the shader, it uses this texture coordinate, which is an interpolated value. And then it uses that interpolated value to look up a new value, get the color from that texture, from that coordinate, that UV coordinate within that texture, right? Gets the correct texel from the texture. Now, notice the texel, one reason to refer to it as a texel is it might not actually be a one-to-one thing that was in the original texture. You can do things like use mipmapping. We'll talk about that in a second. It's a way to basically have better quality at various resolutions, or have different sorts of filtering that are going on in between that sampling, right? The sampling isn't necessarily just grab an exact pixel. It might be an interpolated pixel. It might be something that is filtered according to some sort of filtering, or so on. We'll see that in just a second. So we have a question. I'll hold on for just a second. Catch my breath. Maybe have a sip of. Questions are great because it at least gives me a chance to pause. Okay, what happens if you try to calculate a texel outside the range 0, 0, and 1, 1, like if you tried to sample at -1, -1? Very good question. There are a number of different modes that you can specify for when that happens. You can do things like have it automatically wrap around, or automatically say, well, okay, anything outside of 0, 0, and 1, 1, you get the same exact pixel as if it were on the edge, right? Or it may repeat, or it may reflect, or it may, there's a couple of different modes, right? So you can set up the sampler to do the right thing according to how you want, right? So it will generally map it within 0, 0, and 1, 1, either by clamping it or repeating it, or something like that. You have a couple of different options. We'll see those, I think, in a bit. Good question. All right. So the textured pyramid, this is kind of what happened. We can use the normal brick wall and map it this way, and you can substitute. You should try this. Once you load a texture, then try to find another texture. use another texture, load that in, see what happens. Okay. So it's easy to swap textures once you have, once you have the code, basic code written. It's easy to swap in textures because of that 0 to 1 kind of range. You're not worried about the exact size. So there are some issues, potential issues, that have been well thought out nowadays, that do often result in texture artifacts. And by artifacts, we mean sort of just basically think of glitches in their representation, because if you're familiar with sampling in general, you may have heard of things like the Nyquist theorem. Have you ever, or the Nyquist rate? Hopefully I'm remembering that correctly. Okay, now this used to be the sort of thing that would be covered in communication systems. Are any of you familiar with sampling theory? No? Okay. So, well, brief introduction. Okay. If you have some phenomena or some wave, some sort of thing, some image, some sound, this shows up in audio a lot. There's where most people have probably been exposed to it, right? We hear about the sampling rate of audio files. You may have heard, an audio file is 44,100 samples per second, right? So let me get just a general, right? You probably have heard someone refer to, whoops, not Giphy, that's not right at all. Poll, there we go. You hear about 44K audio. No? All right. So the idea, if you're familiar with audio, you hear, is audio 44K or 192K or, there's kind of these really big numbers. Now, humans can actually only hear up to about 22 kilohertz. The highest sine tone, highest frequency we can typically hear is about 22 kilohertz. Way above, sort of what you would think of as, the notes on the piano or scale or something like that. But it's the highest sort of frequency that we can hear. So you'd say, well, okay, if we can only hear that high, why isn't like our magic numbers in audio something like, well, we'll just do all of our audio at 22K because it's 22 kilohertz, 22, to sample it at that same rate. And it turns out that in order to represent something digitally that is a recurring signal, you generally need to do something. You need to sample that signal at twice the rate at which it could potentially vary. Okay, so if we have a sine wave that was playing at 22,000 hertz, 22 kilohertz, we would actually have to sample it at double that, 44 kilohertz, in order to not to kind of just catch the fact that it's a sine wave or an actually oscillating wave. Otherwise, you might always pick the high end of the wave, which I'll show in here. Like, imagine we had this sine wave here, right? So this sine wave is up and down at some certain rate. Now, if I sampled it at exactly a certain rate, like say I only sampled it at this point in time, and then this point in time, and then this point in time, and so on, I would never notice the fact that this actually was an oscillating waveform. I would think that it was just solid 1 up here because I'd be sampling it here, and it was always 1 when I sampled it. So I would lose all the information that's down in here, that's the fact that it is actually oscillating back and forth, because I'm kind of sampling it at a frequency. I'm sampling it often enough that I miss the additional information that's kind of going on, okay? So what does that mean, right? You have a certain rate that you are looking at a signal, potentially repeating signal, and you have to look at it at a certain rate in order to correctly sort of digitally represent it and kind of come up with a thing. Like, imagine you had a checkerboard pattern, right? So the top of this is, say, white, and the bottom of it is black, right? White, black, white, black, white, black, white, black. And if I sampled it at a bad rate, like what if I sampled it just here, 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 I would wind up with, instead of the white-black oscillation, I would see just white, right? And then if I said, well, okay, what if I sampled it half as fast? I would still see white, 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 white. I'd never see those black pixels unless I started here. Then suddenly, okay, if I sampled it the other rate, I'd see black, 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 right? So there's this potential mismatch in between here, right? If I was looking at a checkerboard pattern that was a high resolution texture that I then wanted to convert to another rate, because when I'm sampling something, I'm basically doing a sort of a conversion. I might say, okay, the original texture is a 4K texture, a big, nicely, wonderful, fine, detailed texture. But I ultimately want to put it on a polygon that is only, maybe it winds up being, it's a tiny little square that's 2 pixels across. So which 2 pixels do I choose that actually represent that larger texture, right? How do I account for that, right? So texture artifacts occur when texture image resolution is either too low, right? You see things that wind up being blurry or stretched, and that's what you're kind of used to seeing, right? If a texture image is too low, your game looks sort of just, crunchy or blurry, that you're used to. But there's this other case where if your texture image resolution is too high, you can also wind up with artifacts because of these sampling errors that I just sort of rambled on a bit about, right? Because what's happening is this thing called aliasing, right? How many of you have ever seen kind of an optical illusion? Here, I'm going to give you, this is a good one. This is a really good optical illusion. I have to share this now that I thought about it. Wish I'd thought about this ahead of time. But it's well worth it. Well, let's see if I can find it now. All right. Here it is. Here is a picture. Here's an image, hopefully. Can you all see that? This helicopter appears to be hovering while its blades are not moving at all. Right? So the blades are not moving at all. Now, of course, that's not what's happening. That'd be silly. That clearly the helicopter's blades have to be rotating in order for it to be lifting. But if I only look at it at a rate that is exactly the same, it just so happens to be exactly the same as the rate that it rotates, then I wind up missing the fact that it's rotating, that it's changing, right? So I see this still version. Now, it's not motion that we're talking about here, but it's the same sort of phenomenon, right? That you wind up, anytime you are trying to sample something, whether you're trying to spatially sample it or temporally sample it, right? When we're texturing, we're basically doing spatial sampling. And if you don't sample it at a good enough rate, you wind up with losing information or presenting sort of the wrong information. Like suddenly your black and white checkerboard winds up being nothing but white or nothing but black or some weird moire patterning as well, right? Moire patterning is another fun term to look up if you're familiar with that. M-O-I-R-E pattern. Okay, and this is sort of, I get some good images for moire patterns, right? Stuff like this, right? Which often happens because you're trying to sample something according to whatever the resolution of the device that you're at is capable of. But the original image may have had more information in it, right? So we wind up with these kind of interesting artifacts, right? So you may have seen those sort of things on certain textures these kind of weird patterns and older hardware. Right? Whoops, that's not a poll. Ha! Well, go ahead. Give me a thumb. Just go ahead and react to that one if you like. If you've ever seen, this is the sort of things that, sometimes, especially if you've seen other older video games or other older graphics, you may have seen things like that. Okay. So here, we'll get past this slide now. This is all, a lot of the times, this is because of sampling errors or aliasing. So here's an example of aliasing. The original waveform is red. The reproduced incorrect waveform is the blue one. And this is a really crazy case where, okay, the original one should have been this high frequency one, but because of the sample rate, right, it only sampled here, 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 at this fixed rate, and it came up with this other way different. Now the shape is the same, but the frequency of this wave is very different than the original, because the sampling rate is really determined by the resolution of the polygon of the triangle that we're actually rendering on the screen, right? That's how, like, if we went with a very small one, or you wind up with a very stretched set of UV coordinates, you wind up with something that potentially is a lot lower or higher resolution than your texture actually was at. That's why this is potentially happening here. Okay. So here's an example of it that you may have seen in it if you had, go find a PS1 style game, and the people are doing PS1 style retro survival horror games. That was a big thing. Who knows, with Halloween coming, maybe we'll see a bunch of those happen again. So you can see this weird thing happening where all of a sudden we have in the foreground things look fairly normal. We have this checkerboard pattern, but then they start to do this sort of moire thing. And in this area here, we get to the point where the resolution is low enough where now we start hitting that nothing but, our checkerboard now is then missing one whole layer here. So we miss this stripe, we miss this stripe, we miss this stripe as it gets further out, because we just don't have the resolution to represent the checkerboard at this location here. We're only seeing every other line of a much, much lower resolution checkerboard. And because we're only seeing every other line, it then suddenly switches to this sort of just what looks like stripes. Okay? Because we just don't have enough. Here we are sampling more than every row, right? So as things get pushed into perspective, fewer and fewer rows are represented in the distance here. Here, this square is represented by, I don't know how many how many rows of pixels. Where way in the distance, one of these squares might be represented by, very few number of pixels. You also see it as a sparkling effects when objects are animated. You can also even see it sometimes on your television set, depending, now that's why 4K, 8K, higher and higher resolution TVs are great, because you wind up, less and less of this sort of visual artifacting in addition to the resolution. But on older sets, older digital sets, you may sometimes see, or even older content on digital sets, you may see sort of sparkling as you see, screen doors pass on an image and so that sort of thing. So that's what's happening there. So how do you deal with that? How do you work to make that work out, right? Technically, you have more than enough information in a high-resolution texture. You shouldn't have a problem. All the information is there, right? What we need to do is we need to do some either calculate and filter the image so that we could say, well, okay, if I wanted to represent this whole image in 1 pixel, for example, if this whole texture here of this gentleman, I forget if this is a Clevenger or it's one or the other, I think. If I wanted to represent him as a single pixel, I would really need to say, well, let's take the average of that whole image, and that would be the best representation of this image as a single pixel, right? And that's one approach, to actually calculate that depending on, figure out, okay, for this particular polygon, what is the best resolution of the base mesh, and then, resample everything, scale it so that it represents the perfect potential sampling source. That's expensive, right? Really doing that sort of calculation, that sort of filtering is going to be expensive. You don't want to really do that unless you have to. Or maybe someday it'll be so cheap to do things like that, maybe. One of the options that we currently have, though, and this has been around for a reasonable amount of time, and thankfully used to have to do this by hand, mipmapping. And this is a multi-image, oh wow, off the top of my head I'm forgetting what MIP stands for, but it's basically you're taking this, you take an image and you create multiple resolution versions of it. You create a tree that's at various resolutions, so that depending on how big the polygon you're working on, what sort of sampling basis you need, you use one of a number of scaled versions of that image. And it's, the structure is basically, sort of half and half again and half again and half again is how they decided to do this, right? So you see, like, this red square here, each red iteration is basically a quarter of the original here. So this one, and then you get a quarter of it here, and a quarter of that one there, and a quarter of that one, and quarter and quarter and quarter and quarter, right? It's quarter because it's half in each dimension. Half in each dimension gives us a quarter in the total dimension, total area, right? So you can imagine here we have red, green, and blue. So this is a fairly efficient way to store this multi-resolution of the texture image files stored together. Now this does require 33% more storage. So it's not free, but it is reasonable. You may not need it for every texture that you're working with ever, but if you are going to be scaling things on the fly, and this is mostly a real-time graphics issue, all right, if you weren't worried about real-time graphics, you would just scale it and do the right thing. You'd filter it and whatnot. But this is one that shows up, this is a real-time graphics optimization, right? So if you were just in advanced graphics, you may never hear about mipmapping. So this is the bonus you get from being in interactive 3D computer graphics, I guess. All right, so that's mipmapping. And OpenGL will generate mipmaps for you. Thank you very much, OpenGL. And it'll do the right thing. Now you can see it does sort of look blurrier as it goes in the background, and that's because it's being sort of filtered like that. But it looks correct, right? Black and white is averaging out to gray as it gets way in the distance there. Things are looking generally like they're doing the right thing. It's a little bit funky, but it's doing the right thing. So we can choose whether or not we want to generate mipmaps, and then we wind up, it's going to do some of the work for us, the heavy lifting in terms of figuring out what mipmap level to use, potentially. So we can bind a texture just like we did, but we can also set it to be using mipmapping. And there's a number of different ways. You can also say, what sort of filtering are you doing to generate the mipmap? So here's a linear nearest neighbor mipmapping. So it's kind of the fastest, cheapest version. Nearest neighbor, linear filtering. And then you go ahead and you can generate a mipmap based on there. Okay? And then OpenGL will automatically use the resolution in the mipmap closest to the region being drawn. Right? So depending on what size it needs for that region, it will automatically choose the right mipmap for you. It's not necessarily 100%. It can sometimes produce artifacts. These vertical lines suddenly change from thick to thin at the mipmap boundaries if it's not careful, right? Because it's like right at the edge of one mipmap and the other, right? So you can wind up with kind of odd situations if you're not too careful. You can use different types of filtering. Filtering of the mipmaps so that you wind up with kind of smoother transitions between them. So minification is part of the mipmap process, which is a filtering. There are different types of mipmap filtering. The nearest neighbor. Choose a mipmap with resolution most similar to the region of pixels being textured. Obtain the nearest, right? This is the nearest texel to the desired texture coordinate. Yes, that's right. It's basically a level of detail for textures, right? It's adjusting on the fly, adjusting the level of detail depending on how large of an area it really needs to fill with that texture, right? Level of detail modeling is more, most of the time when you're dealing with LODs for models, it's more as a sort of resource issue to be using different resolutions, because you don't want to have a very complex version of a spaceship. It's way in the distance and it's only represented by a single pixel. So it makes sense in that case to use different versions of things, but it's sort of similar, right? It's the GPU, it's the system working together to kind of pick the appropriate resolution depending on how big something's being rendered. In some cases, it's to avoid visual artifacting. Other cases, it's to kind of optimize efficiency and performance. Right? So here are the variety of, wow, it is already 1:20. So I'm going to keep going, and then we're just going to probably finish up. We're going to do more or less lecture stuff all today, and we may bypass the check-ins today if we wind up see if I can get through this and then talk a little bit about IMGUI. So let's try to get through here. Okay, leave this to you read with regards to the various types of bi-filtering, linear filtering, nearest neighbor filtering, trilinear filtering. This is basically going to be how smooth you want, or what type of filtering you can do to smooth out the mipmaps and pixels generated. All right. So here's a demonstration of what's called trilinear filtering. It's sort of a three-way linear filtering where you are using two levels of mipmapping and averaging across a group of pixels. So you have filtering in 2 dimensions. Three dimensions. You have a one level of filtering that is basically in the different level of detail, for lack of a better term, and then also averaging within this particular. So it's as if you were able to generate another level of detail averaged here and averaged here to kind of come in between. So that's the most expensive. Trilinear filtering is going to actually kind of average these 4 pixels together, texels together, average these 4 together, and then interpolate them in between. So that gives you a sort of like, you're getting close to really calculating on the fly exactly what they should be using according to smooth scaling. Okay, anisotropic filtering, AF. So mipmapping can result in loss of detail when an object is tilted because of perspective, right? Because its primitives appear smaller along one axis, width or height, than the other, you can get this sort of odd detail loss when you tip or you tilt a particular polygon and you have to sample it in perspective like that. So we have this technique called anisotropic filtering, where it will mitigate the loss of detail while still reducing aliasing and sparkling by sampling the texture at various rectangular resolutions, such as 256 by 128, 64 by 128, and so on. So it will apply this anisotropic filtering to say, automatically it will figure out how tipped a particular polygon is at with regards to the texture, and kind of generate some extra resolution in there. Well, not extra resolution, but more appropriately filtered detail according to the tilt of the resulting texture. And that is expensive. And not all graphic cards support it, but it can be very effective when it is used. Okay, so we have all these different ways, anisotropic filtering, mipmapping, and so on, to make sure that textures look correct at the level of detail, at the level of resolution, and even at the angle and perspective that the texture is being used at. Right? So there's a lot of heavy lifting going on in the card with regards to kind of just different techniques you can do to make textures look good. All right, here's an example. So you can see in the background here, we wind up with what looks like lots of good detail in the front, but then as we go to the background, everything gets blurrier because we're using lower resolution. So instead here we can do things like say, well, use the higher resolution except for the fact that, you know, higher resolution in the front, tip it towards the back, and wind up reducing the loss in resolution by adjusting that, or adding that filtering in according to this algorithm on the fly. So we're going to preserve detail as we go on. So here's mipmapping without an isotropic filtering. Here's mipmapping with an isotropic filtering. Kind of cool. Hardware is great, isn't it? You had the question before. I believe it was also Palmer. No, Owen. No, Palmer had mentioned. What happens if you have texture coordinates outside the 0 to 1 range? OpenGL has several options for you. You have repeating, right? So it's just basically going to truncate and then, or you know, use the remainder and figure out, okay, that's what it would have been. So if you said 3, that becomes 1. If you said 3.5, that becomes 0.5, and it's going to map appropriately across the triangle. You can also use a clamp to edge, so 3.5 would become 1, right? You can see here's the original texture in here. Anything that goes beyond is just clamped to whatever it would be at that edge and stretched out. Or clamped to border, meaning anything outside has some sort of border color that just gets mapped by default here. Right? So you can set those things according to here. A couple of different options: repeat, edge, and clamp to border. Right? And there even is this mirrored repeat version where we can say, okay, every other, yeah, doing it right here, you can see he's actually looking, I think, opposite directions between each one. And upside down, yeah, so you can tell as well. So he goes here, and now he's suddenly upside down, and then he's upside up, and so on, because he's using repeated, mirrored repeating. Very cool, right? Whew. Last slide, good. Okay, so perspective distortion. We have another option, another thing you can specify to get textures to look just right. So we have this perspective distortion. OpenGL automatically will correct perspective distortion as tilted objects are textured in 3D space. Okay, so there's a calculation that's going on as we get tilted and where we would wind up choosing the texture from. Here's without any correction, right? So as it's tilted here, our sampling is going to become problematic. OpenGL will correct for that, depending on, you know, to apply the perspective that you're tilting at and interpolate correctly according to that tilt. You can disable it if you want. You can say no perspective, out, vec2, right, to tell it, okay, do not apply the perspective correction with regards to your texture sampling. If you needed to do it in the vertex shader, this is it going out from the vertex shader, because remember, the vertex shader is what is telling the fragment shader, that's why it's out of the vertex shader, right? The vertex shader is pushing texture coordinates out. So you can say no perspective out vec2 text coordinate. Or in the fragment shader, you can tell it no perspective in vec2 text coordinate to tell it, okay, disable that as far as this one goes, as the fragment shader goes. All right. That was a whole bunch of stuff about basic texturing and all of the extra hard work that that OpenGL does for you to help your shaders look correct and make your texture mapping look correct. There's not an awful lot of examples. It's really just this this chapter has just a few examples in terms of the programs, so you can kind of probably get through those relatively quick. And so do follow along in the text on there. What we'll do today is, if we do, I'm going to wrap up a little bit early and give you more time to kind of just go through the tech stuff to kind of make sure you go through here, so that, you know, when we meet later on in the week, it would be great if everybody sort of had the chapter 5 texture stuff behind us, and then we'll kind of see if that makes sense. We'll see where we're at later in the week. All right, so last but not least, I want to mention this. And I've become a huge fan relatively quickly of IMGUI. And I've used IMGUI before, but I think IMGUI is just such a great thing and resource that I would like you to adopt IMGUI in your projects sooner than later. We use IMGUI in game engine architecture as well, and it actually is used in all sorts of different applications. There's some different examples I pointed to there. Simple introduction to Dear IMGUI library. This is a really good resource. I posted a link to that. So I wanted to give you sort of a quick example. I went ahead and incorporated IMGUI into my textured plain red cube here. And I think last time around I just, how much have I demonstrated? I think I at least showed opening a window in IMGUI, but I don't think I showed it really doing anything interactively, right? I'm either that or I'm now forgetting myself. I should rewatch my own lectures. But let me open up the plain red cube here. Windows and sliders. Okay. Did I have it controlling anything yet at that point? I don't know if I did. That's a question. Anyway, let's assume that I didn't, and we'll all win today as a result. So here's the plain red cube. It didn't control anything, but I explained. Okay, good. So let's show it actually doing something, if I haven't broken anything. So here's IMGUI, and it is the plain red cube demo, but here obviously my plain red cube is not red. Okay, and here's my IMGUI interface that is hovering above things, and I can decide, okay, well, let's see, let's make the cube red. So I can just set green to 0 and blue to 0, and now it is red. Okay, I can also click on that color and decide, let's see, let's move this around a little bit and make it sort of pale, you know, kind of a salmonish, pinkish kind of thing if I wanted to, and then close that, right? So interactively now I can change the color. Obviously a lot cooler than having to go back and change the code back and forth and back and forth. Similarly, you'll see I have 3 sliders here. I also have a little text, hello ComputerGraphics, really, really easy to add. I have a set of sliders for position, which is X, Y, and Z, back and forth. Now I have a camera tilt in here, which is not controllable here. So these are actually the model coordinates that are changing, right? So the camera relationship to the model is not changing as a result of this, right? We're changing the model in the world. The other cool thing I can do, of course, is to actually rotate, to do a rotation. Here I am flipping it in the X, the Y, and the Z. And it's a little tricky to see depending on how I've moved things and how I've already rotated. So let's see. For some reason, I have to figure out, is there a way to easily get that to be set back to 0? No. All right, now there's no shading going on, which of course is why this doesn't look particularly cool. As we get into shading and lighting, sorry, it is using shading, it's just not using any sort of lighting. We will be tackling that in chapter 7. So let's see. So here's our X sort of tumbling, Y rolling, and this one looks kind of similar. Now, how much code goes into there? How terrible was that to actually implement? Well, if you follow the examples, it's actually pretty straightforward. I'll show you. This is just a few lines of code, really. The main thing is that I'm including the IMGUI code directly in my project here, right? I'm using IMGUI draw, IMGUI GLFW, because that's our windowing library that we're using, OpenGL 3, same for OpenGL 3 and 4, and then I have IMGUI widgets. So in my main program, I have some simple setup. Now, if you are using this, one thing you have to be careful of is where the screen gets cleared. So in our examples, usually the display routine itself also has GL clear, sets the buffer bit, that's a little redundant, and then sets the clear color to be like the black background. So if I called my IMGUI routines and then my display routines, I would wind up clearing out the IMGUI routines, which is no good. So in my example here, in my main program, in my loop, I actually display my cube, and then I do all my IMGUI stuff. And I create a new frame, I show the frame, and then I have a few things I add, right? I give it's a title for the menu, I give it a little bit of text, and then I have a slider, which is my rotation, a set of 3 sliders that are clamped to a value between -2 and +2. That's for the position. Then I have a set for the rotation. And then what I do is I copy those values that are returned. They are returned in an array of floats. And then I plug those into my cube location XYZ and my cube rotation X, Y, and Z, which are, of course, the values that go into calculating my transformation matrices. One thing to mention that's kind of cool, if you haven't looked so far into rotations, the way that normally the rotations are done in OpenGL using this rotate in GLM, what we are specifying is a angle of rotation and the axis around which we are rotating. So we're using an angle and an axis. So to rotate in X, I do this. To rotate in Y, I do this. I say, okay, how many degrees or how many, the angle, and then the axis to rotate around is this 0, 1, 0. And then to rotate in a pure Z direction, or around the pure Z axis, I would say, here's the Z rotation, and the angle, or the angle and the axis, right? If I wanted to rotate it diagonally around a diagonal axis, and I didn't want to use the 3 of these, I could actually do things like say, well, rotate around this axis. That would say rotate around the diagonal. But I don't want to do that because I want to maintain my simple Euler interface, which is my rotate X, Y, and Z. So if you're ever wondering how you could use rotate here and still specify X, Y, and Z, you just use a set of vectors that are X, Y, and Z. Anyway, that's besides the point. So that is what's done in here, and then ultimately at the end I say IMGUI edit, IMGUI render, and pass the rendering the draw data so that it gets rendered correctly. The setup is all pretty straightforward. We check IMGUI's version, we create a context for it. It's past the same window that we created up in GFLFW. We have some initialization. This can be lifted from any of the tutorials, basically. Especially that, is it Conan? I think his name is Conan. His tutorials, you can lift that right from here. Now, here'd be one challenge that I would love to see. I haven't tackled yet. I'm going to try to do this at some point when I have some time. Is you may have noticed that we are loading shaders in on the fly. Basically, at program time, at runtime, we are loading shaders and doing different things with them. There's no reason that during the course of a program you couldn't load another shader. You couldn't, destroy a shader and add another shader. So here's a challenge I'll throw down, and I'm going to try to do it, and I would challenge you to do it as well. With IMGUI, you can have a text field, and there's no reason that you couldn't write a shader in that text field, and then use that as the source code to pass, compile, link, etc., into a shader. So the challenge, if you so choose to accept, and this, this would be one part of, worth some points on a project, I suppose, would be to interactively allow for shader compilation. So you could rewrite your shaders while your demo is running. Now, this might be the sort of thing, if you were writing a game engine, you may want to be able to, write your own shaders on the fly. And you could certainly even write a shader and then save it out to disk if you wanted to. Use it for other programs. So you could use this as a way of interactively developing shaders. Throw that down as an example, as a challenge. All right, so that brings us about, we're at 1:40. Normally we would end at 2:10, so we're about half an hour early. People mentioned being tired. I think I mentioned being tired as well. So what I'd like to offer up, rather than go through the check-ins, is kind of open this up as a little bit of lab time. If you haven't already caught up with Chapter 4, go ahead and do that, asking any questions, and we'll use this as kind of open lab / studio time to be thinking about your projects. If you have any Project 2 ideas and you want to ask about them, please also do bring that up. But I'm going to end the lecture portion there, unless there are any other lecture questions. Okay. So let's take a quick look down memory lane here with regards to when the project is due. That's not the schedule. There it is, ComputerGraphics Fall 2020. And Project 2 is due basically, we'll call it Monday, October, that'd be 10th, 11th, 12th. So you got a good chunk of time. Okay. There's a good chunk of time. We technically said on the schedule, it said after Friday, October 9th, which is going to be October 12th. Right? So that gives you a good chunk of time to do some cool stuff in. So I would like you to, before then, shoot me a direct message if you have, particular questions, ideas, proposals, sort of a. So when will future check-ins happen? I'm always going to leave open the possibility of check-ins. So just because I don't want to, basically everyone today is going to get. What I'm going to do throughout is every check-in group will have one day that winds up being skipped. How does that sound? So that will be fair across the map here. So we're going to maintain our schedule, and I think the best thing, what I will do at some point this week, is I will post the check-in calendar with actual dates on it, so that you can always kind of refer to that one, and you'll know what week it is, and so on. I just basically, between 3 and 4 and the first projects, I think, everybody, I haven't posted the grades on the first project. Everyone, I did check in with everybody on the first project, I believe. So there were a few people who were going to look into fixing a couple of things. But with regards to, you will know, who you are. And everybody else, don't worry, you did fine. I think I believe I told you did fine. So grades will be at some point, probably by next Monday, the grades will all be up there. I'll be caught up on the posted grades wise. I'm kind of giving some people a chance to kind of catch up again. Slight hand waving, slight vagaries. Hopefully that's okay. All right, let me stop the streaming. I didn't really intend for the streaming to have this much, but so it goes.